the recording. And today's lesson is going to be about confidence intervals and sample size estimates. Just one quick note, I have changed the time for my office hours this afternoon from 1 o'clock to 3 o'clock. My husband is unable to drive and my daughter gets out of school at 3:20. So I couldn't run until 4 o'clock, so I just backed them up an hour. So if you need something between 1 and 3 today, I'll be in Zoom and the link is there in the announcements. I also sent an email out to everybody. But the topic today, continuing in Module 2, is confidence intervals and sample size estimation. And confidence intervals is a topic that is discussed in Stat 1401 if you've had it recently. If you had it many years ago, that was not an initial topic that we included. So this may be new information to you. And we will ultimately talk about, three different types of confidence intervals. We have a Z interval, a T interval, and then we have a Z for a proportion. So we'll ultimately talk about all three of those. My goal today is kind of to give you a broad overview of what is a confidence interval, why do we want to use them, and then also, if we get that far, we'll talk about how to estimate a sample size, how to make sure that we select a large enough sample to ensure that we have a particular margin of error. So I want to begin kind of with an explanation to try to make some connections for you from things that you have previously learned either in this course or in Stat 1401 with confidence intervals. So if you've looked at the PowerPoint, that's why there's a blank slide here, because I want to draw in the picture, which is an explanation, and it wouldn't make sense if you just had the picture on your own. So if you go back to the course in the beginning of statistics, specifically Stat 1401, we talk about the fact that there are two different branches of statistics. The first branch is descriptive statistics. And if you'll notice that that is the adjective form of the word describe. So with descriptive statistics, we are simply describing the data set. We are going to state just the facts, ma'am, just the facts. Okay, we're making no assumptions whatsoever about the data. We can tell you how many were in the sample. You could tell me the maximum, the minimum. You could calculate the mean, the median, the mode, range, standard deviation. Those, we could calculate all of those descriptive statistics that we talked about in the second lesson of Module 1, as well as talking about missing data and outliers at that point. So descriptive statistics is kind of the area or the branch of statistics where you're giving me the facts. You are describing the data set to me without making any assumptions whatsoever. The other branch of statistics, which we're going to kind of be getting into more so today than we have in some of the other lessons, is inferential statistics. Inferential is the adjective form of the verb infer, where we begin to make a generalization about what we know and apply it back to the population. But in order to do that, we begin to make some assumptions about the data set. Now remember, ultimately, kind of the way statistics works or research works, we select a small subset of the population, which we call the sample. And we're able to learn about that sample. We're able to determine those facts. How many were in the sample? Again, what's the minimum? What's the maximum? What's the mean? What's the mode? And then ultimately what we do is we take what we learn about that sample and we want to apply it or infer back to the population. I want to take what I learned and I'm going to apply it to the population so that I can say, because the average age of a GHC student in fall semester 2022 is, let's say that again. Since the average age of a GHC student in Miss Ralston's Stat 1401 class is 21 years old, then or therefore the average age of a GHC student in fall 2022 is 21 years of age. We take what we know about the sample and we apply it and generalize it back to the population. And to this point, when we have been doing that, when we have been finding those descriptive statistics, again, that we focused on in the second lesson of Module 1, we have been finding or calculating what are called point estimates. Okay, where that we are using a single value to indicate the mean or the median, the range, the standard deviation. But what we're going to look at today is, instead of relying on a single value, because if you think about that like a target, having that single value means that you've got to hit that bullseye every single time, that you're using that one individual point, and you're gonna be hitting that target. And that's such a small point or a small value, you don't have any margin of error or any leeway. And usually probably the value that we've calculated is the value for the sample, but it may or may not be the value for the population, but we're going to be close. But again, you don't have any wiggle room. So what we're going to look at today is we're going to begin talking about interval estimates. And with interval estimates, we're going to get basically a range of values instead of a single value. You're going to basically have a minimum or a lower bound and a maximum that your value could be between. So again, if you're thinking about it from that target perspective, you get a little bit bigger area to aim for. Okay, so it gives you some wiggle room. And there are reasons why you would want to do that, why we would want to use a point estimate versus an interval estimate. I'm going to give you some examples a little bit later of where it's used in the real world, so that you can kind of see where we would think about using an interval estimate as opposed to just a point estimate. Now, I failed to mention, but let me go back and mention this. The two, even though we look at descriptive statistics and inferential statistics as two separate branches, they are interconnected, okay, because we need the descriptive statistics, that description, the facts about the data set, to be able to infer or generalize back to the population. So even though it's two different branches, those two branches are interconnected. Okay, so we're going to talk about and focus on these interval estimates. They're called confidence intervals. Okay, they're called confidence intervals. And again, it's just a different type of estimate that instead of being one number is going to be an interval number. It gives us a range of reasonable values in which we expect the population parameter to fall. Typically, confidence intervals are created or can be created for either the population mean or the population standard deviation. Those are the two where you'll see confidence intervals created. In this course, for our purposes, our focus is going to be on the mean, or also a proportion, which allows for the use of percentages. But we're not going to talk about standard deviation confidence intervals. So again, the confidence interval gives us that range of reasonable values in which we expect our population mean to fall or be. But there's still no guarantee that for that given interval that the mean actually falls into it. But we have a predictable probability of success, aka confidence. That's kind of why they're called confidence intervals. They're intervals because we have a range of numbers. We call them confidence intervals because it is connected to a predictable probability of success. We know what kind of success rate we're going to have, that the mean or the parameter is going to fall within that interval. The form of a confidence interval, we use the point estimate, okay, and for us that's going to be the mean, and then we add and subtract the margin of error, again, because ultimately you have to have a lower bound minimum and an upper bound minimum. And so we take our point estimate and then we add to get the upper bound and we subtract to get the lower bound. And we're going to talk about Minitab is actually going to do that calculation for us, but I want to make sure I give you a little bit of background information. So I want to talk about the margin of error for a minute. Okay, I've given you an example here. This is from the 2016 Republican presidential primary, and they had done a survey. And if you'll notice down here circled in the bottom left-hand corner of that figure, it gives the date, and then it says plus/minus 4.8 or maybe 4.9%. It's a little blurry, but that is for this particular poll that was conducted by the Wall Street Journal and NBC News. That is your margin of error, meaning the numbers that you see for Ted Cruz, Donald Trump, Marco Rubio, and so forth, that those numbers could be off by as much as 4.8%, so almost off by 5%. And so that's an example of where you might see the use of the margin of error. You see that a lot, especially in the reportings of survey, because you have to allow for the possibility that your numbers are incorrect. So the margin of error is also called the error bound for the population mean. We abbreviate it EBM, and I'll show you why, okay, because it's error bound for the mean. Okay, so it's abbreviated EBM. And we calculate that margin of error based on the confidence level that we're going to use. How confident are we in our results? And the adjusted standard deviation, meaning we've applied the central limit theorem, because we're going to be looking at a group of items instead of a single individual item. Now, Minitab is going to calculate, sorta, the error bound margin. We have to do a little bit of calculation ourselves by hand, but for the most part, Minitab is going to calculate it for us. You don't have to calculate that margin of error or error bound for the population mean by hand. The confidence level, got to get all the pieces going on here. The confidence level is the probability that the population parameter is within the given calculated interval. Okay, so that's the confidence level, is the probability that the population parameter, in our case the mean, falls within that given calculated interval. I kind of think about it as being the probability of a success that is in the interval, and it is usually stated as a percentage. And it could feasibly be any percentage between 0 and 100%. But typically you want your confidence to be, quote, high, okay, because you want to make sure that you're correct. And so normally you'll see higher percentages for the confidence level. Some of the most commonly used are 90%, 95%, and 99%. Of those three, 95% is probably the most popular or the most often used. We tend to see 99% used, especially in, say, medical research, where perhaps the outcome can be life-altering or life-threatening, if it's like a new medication or something. And so we use the higher confidence level because we want to make sure that we are correct. Okay, so again, I wanted to kind of give you an idea of where we use confidence intervals. And so I just Googled and found several examples. Biologists use confidence intervals to estimate the mean height, weight, width, diameter of different plants or different animal species, which could include humans, because technically we are mammals or animals. You see it a lot, and I know I have another one. Where did it go? Why won't it come up? Well, all right, I think I'm stuck, guys. Let me stop sharing for a minute. It gets itself stuck sometimes for some reason. It gets moody. Won't let me get out of it. Okay, so let me go back to sharing. I don't know why it does that, but okay, so we had biology. We also have like clinical trials, anything related to research, maybe for a new medical device, some kind of treatment or some kind of medication, to determine the mean change in blood pressure, heart rate, cholesterol, etc. Again, for some kind of new treatment or some kind of new drug. Even in the realm or the world of business and marketing and advertising, companies may use it to determine if a new advertising technique, method, or whatever produces significantly higher revenue. Or even in manufacturing and engineering, engineers use it to determine if some new process or technique causes a meaningful change in the number of defective parts. Because obviously we know if defective parts, if they can't be used, then that's costing the company money and therefore cuts into their profit margin. So they want to make sure that that's not occurring. So that's just some uses of confidence intervals that you might see in the real world. But we're going to turn our focus specifically today to the Z interval for the mean. Okay, the Z interval for the mean. Again, there ultimately will be 3 different confidence intervals that we look at. The first one is the Z interval for the mean. The second will be the Z interval for a proportion. And the third is a T interval. Now, we are not going to do all of those today by any means. We're going to get started with Z interval for the mean. And then on Tuesday, we'll look at the others. But the Z interval for the mean, the clue that I need to use the Z interval for the mean is that I am given the population standard deviation. Okay. So when you're thinking about the Z interval, there are a couple of things you want to think about. There are two conditions that have to be met in order to think about conducting a confidence interval, specifically a Z interval. And that is that you have a simple random sample, which typically will be somehow indicated in the scenario. It may actually use the word simple random sample. It may simply say something like randomly selected, but it's usually indicated, or if it's not indicated in the scenario, for our purposes, we make the assumption that it is. And then our sample size has to be greater than or equal to 30, or we have to know that the population is normally distributed. Okay, so if you know it's normally distributed, you're good to go, regardless of the sample size. If you do not know that it's normally distributed, it's some unknown distribution, then your sample size needs to be greater than or equal to 30. And so you're given a scenario. It's usually in paragraph form, 3 to 4 sentences, but in that paragraph, for the scenario, you're going to be given 4 pieces of important information. You should be told the sample mean, the population standard deviation, the sample size, and the confidence level, which is typically stated as a percentage. Those scenarios or the problems related to a Z interval can be provided or displayed in 2 ways. One, you can be given the summarized statistics. They'll outright tell you the sample mean, the population standard deviation, the sample size. Type 2, you have the raw data, but with the raw data, you have the ability to calculate the sample mean, because we can have Minitab calculate our sample mean. So we're going to look at some examples in just a minute, but I need to give you a little bit more background information. So on this slide, and I'm not going to really read the slide to you, but this slide provides the Minitab clicks or steps that you would go through to find the confidence interval for the summarized statistics type 1, but then also how you do it if you have the raw data. In both cases, we have to manually, using our calculator, calculate the error bound for the population mean using the information from Minitab. So that's a manual calculation. But we're going to be walking through these steps, but they are here on this slide, and I'll tell you what slide number it is. It is slide 9, okay, in case you need to refer back to them. To calculate the error bound for the population mean, we take the upper bound minus the lower bound and we divide by 2. And I'll show you why we do that when we get to an example. Maybe it'll make more sense to you. Okay, but please be careful. Remember that to follow order of operations, you have to do the subtraction in the numerator first. So upper bound minus lower bound. I try to emphasize that with the parentheses. You're going to do that subtraction first and then divide the answer by 2. There is a very specific way, especially if you're writing like a journal article or some kind of report. They usually use like an APA style. And so there are specific details and a specific way to state the conclusion. And that interpretation or the inclusion should always indicate your confidence level, what population parameter is being estimated, and what that interval is. And so I've given you here the exact phrasing that can be used. We estimate with whatever percent confidence that the true population mean, and you got to put it in the context of the problem, the true population mean age of GHC students in fall 2022 is between the lower bound and the upper bound, and you want to include the unit. So if it's years or inches or dollars or whatever. And again, I think that'll make more sense as we actually put some numbers in there and walk through the problem. Oh, we're hung up again. Okay, let me start the share back. Okay, so we're going to look at some examples. And I took the examples that are here on the PowerPoint slides and I moved them into a Word document so we could write on them and I can do all the pieces. Okay, so because it is a paragraph, okay, 3 to 4 sentences, we need to read it. And again, guys, you got to be careful and read it carefully. But it says, suppose scores on exams in statistics are normally distributed with an unknown population mean and a population standard deviation of 3 points. A random sample of 36 students is taken and gives a sample mean of 69. Find a 95% confidence interval for the true population mean of statistics exams scores. Now, if you think about the 2 statements that it said we needed to kind of double check, this particular problem tells us that we have a random sample. So it said, you know, the first condition was there is a simple random sample. It tells us a random sample of 36 scores. So it tells us that in the problem. The first sentence, then the other condition is we either have to know that the distribution is normally distributed or have a sample over 30. And in this case, I actually have both because it tells me in the first sentence that the scores on exams in statistics are normally distributed. But then we also have a sample of 36 scores. So I actually meet both of those. I have know it's normal and the sample size is over 30. I don't have to meet both, but I'm good. I mentioned to you that in the scenario, you should be given 4 things. And I think it's helpful to identify those 4 things and write them down. we should have the sample mean, we should have the population standard deviation, the sample size, and the confidence level. I use CL for confidence level. So if I go back through and read this problem, it tells me at the end of the first sentence, a population standard deviation of 3 points. So sigma, my population standard deviation is 3. Continuing, it says a random sample of 36. So my sample size is 36. And gives a sample mean of 69. So my sample mean is 69. Let me get back to my pen. And then it says find a 95%. So my confidence level is 95%. Now, let me remind you that the way that we calculate it, if we were doing it by hand, we would have our point estimate, which in our case is the sample mean. And we're going to add or subtract the error bound for the population mean, or the margin of error. That margin of error takes into consideration your standard deviation adjusted for the sample size and the confidence level. Now I could show it to you by hand, but there's really no need because Minitab is going to do all the work for us. So once I've identified all of the information, I'm going to go out to Minitab. We go to Stat, Basic Statistics. We are doing a 1 sample Z. I am using Z because I know the population standard deviation. What I have in this problem is the summarized data. It's given me the sample mean, the sample size, the population standard deviation, and the confidence level. So in this drop-down box, I choose summarized data. And then it identifies the things I need to enter. The sample size, which was 36, that was given. The sample mean, which was given as 69. So my sample mean was 69. The known standard deviation. Minitab refers to your population standard deviation as known. Okay, so when you're looking at this, the Minitab calls this the known standard deviation, and it is 3. Then I choose options because I need to tell Minitab what confidence level I'm doing. It's 95%. And the alternative hypothesis should be that the mean does not equal the hypothesized mean. Now, just for an explanation so that you kind of get an idea of what's going on, because we know this is normally distributed, you have your bell-shaped curve with your mean, in this case our sample mean, in the middle, and we're looking for this interval, and it could be that my estimate is a little bit below the mean, or it could be above the mean. This would be like taking our point estimate plus the error bound margin. And on the left, it would be the mean minus the error bound margin. And so we know that this region in here, actually it's not that region, it's actually the region in the tails. That's why it's called a two-tail. Okay, that these regions in the tails, okay, we got 95% confident, so there's a 5% chance that I'm wrong, but I could be wrong and be too high, or I could be wrong and be too low. So technically it is what we would call a two-tail, because I could have 2.5% below and 2.5% above. Has to total 5, so 5 divided by 2 is 2.5, because I know I'm 95% confident. So if I'm 95% confident, meaning that's my success rate, there's a 5% chance that I'm wrong, and that is divided into both regions, or between the two regions, whether I'm below or above. So it's a two-tailed test, and we indicate that with the not equal symbol. Little theory, but that's why I'm selecting not equal. For a confidence interval, it will always and forever be not equal, which is the default in Minitab. So then I click OK. I click OK again. And my results appear up here in this screen. Okay, so let me copy this so I can kind of lay it out for you. Okay, so it tells you here that your sample size was 36, the mean was 69, and then here is my confidence level. This piece right here is your adjusted standard deviation from the central limit theorem. Okay, so my 95% confidence interval for the mean, and it does tell me that my known standard deviation. So I have two numbers. I have 68.020 and 69.980. I hope that it makes sense to you that that first number is what we would call the lower bound. Visually, that would be this number here. And the second number is your upper bound, which is 69.980. So my confidence interval has a low of 68.020 and an upper bound of 69.980. I need to calculate the error bound margin. The error bound margin, and that's not the way to write it. The formula is the upper bound minus the lower bound divided by 2. So for this problem, I would have my error bound margin is 69.980 minus 68.020, and then that's divided by 2. Again, please be careful. Make sure you follow order of operations. You need to do the subtraction in the numerator first using your calculator. Okay, so I have 69.9880 minus 68.020, which gives me 1.96, and 1.96 divided by 2 is 0.98. So my error bound for the mean is 0.98, meaning I could be off almost by 1 point. It's 0.98, so I could almost be off by 1 point. Then I need to write my conclusion in the proper form. So my conclusion in the proper form would read, we estimate with 95% confidence, because that was the given confidence level, that the true population mean, and what was our variable here? Mean statistic exam scores, mean statistic exam scores are between 68.020 and 69.980. And if we had units, we don't really have units for an exam score, but if we had units, we would include them. I wrote two words here in capital letters, true population, because those are the two words that students want to leave out when they're writing this conclusion, because we're trying to figure out the estimate for that true population mean. What would it really be? We're estimating it, but what would it really be? You have to have those words in the conclusion. We estimate with 95% confidence that the true population mean statistics exam scores are between 68.020 and 69.980. The primary thing you need to realize is that we're creating an interval, a range of values, as opposed to one. Minitab is going to do most of the work for you, with the exception of calculating the error bound for the population mean and writing the conclusion. Everything else that you need to work the problem is given in the scenario. Do you have questions before we go to a second example? Okay, it says noise levels in area. Oh, mercy, I got a typo. Noise levels at area hospitals were measured in decibels. The mean of the noise levels in 84 hospital corridors was 61.2 decibels, and the population standard deviation, was 7.9 decibels. Find the 99% confidence interval for the true population mean. Okay, here again, it doesn't outright tell us that we have a normal distribution, but it says that we have 84 hospital corridors. 84 as a sample size is greater than 30, so I'm good to go. And I'm going to assume that they were selected randomly, although it doesn't clearly state that. So I've met the conditions. And then everything else that I need for working the problem has been given. I should have the sample mean, the population standard deviation, the sample size, and the confidence level. And again, if you go back and read through the problem, even if you have to, read through it carefully, it says the mean was 61.2 and the population standard deviation was 7.9 in 84 hospital corridors, and we want to create a 99% confidence interval. I'm going to take all of that information and I'm going to plug it into Minitab. stat, basic statistics, display descriptive, I'm sorry, wrong way, stat, basic statistics, 1 sample Z. Again, we have the summarized data. My sample size was 84. My sample mean was 61.2. The known standard deviation was 7.9. Options, I need a 99, so we're going to type 99.0. My alternative should always be not equal for a confidence interval. Click OK. Click OK again, and it gives us the confidence interval. Okay, again, you can see my sample size was 84. My mean was 61.2. My adjusted standard deviation is 0.82, and you get the confidence interval. My lower bound is 58.980. The upper bound is 63.420. I'm reading those directly from the Minitab printout. Then I have to manually calculate the error bound for the mean, which is the upper bound minus the lower bound divided by 2. So I have 63.420 minus 58.980, and that is then divided by 2. Again, be careful. Do the subtraction first. 63.420 minus 58.980 is 4.44 divided by 2. So my error bound margin is 2.22. Then we write our conclusion. Catrice, you have a question?
I just had one quick question. What does the N stand for again?
N?
Yes, ma'am.
Is your sample size.
Okay, thank you.
Okay, so then we write our conclusion. We estimate with 99% confidence that the true population mean noise level at area hospitals is between, we get the number, 58.980 and 63.420 decibels. And there you go. Other questions?
Is the error bound margin, is that the you know, when you showed the example, is that the plus or minus? That's the plus or minus. Okay.
Yes, ma'am. That's the plus or minus.
Okay. So like
so if you
that example that you gave with the polling or whatever, that was plus or minus 4.9, so almost 5. Okay.
Yeah. All right, now let's look at an example where, where you have the raw data. Instead of having the data summarized for you, you have the raw data. So it's the same idea. We're still trying to create a confidence level or interval, excuse me. It says, suppose scores on pop quizzes in statistics are normally distributed with an unknown population mean and a population standard deviation of 2 points. A random sample of 22 scores is taken and listed here, and they give you the list. Find a 90% confidence interval for the true population mean of statistics pop quiz scores. So the only thing that's kind of different about this problem is it does not outright give you the sample mean, but it does still tell you the population standard deviation, which is 2 points. It does tell you that you have 22 scores, because even if it didn't tell you you had 22 scores, I could count up the numbers in this list to know how many I had. And it still gives you your confidence level, which for this problem is 90%. So the process or the calculation is virtually the same. We change the command in Minitab just a little bit because we have the raw data. So I take this list of 22 numbers and I enter it into Minitab, which I did before we started class so that I wouldn't have to sit here and write them down and type. So this first column are those 22 scores, and I can scroll down and see that my last value is on row 22, so I know I've entered 22 values. So it's really the same keystrokes. We do stat, basic statistics, one sample Z, and again we're using Z because we know the population standard deviation. But this time I don't have the summarized data, at least not all of it, because I don't have the sample mean. What I do have is one or more samples each in a column. I have the data set, so I have the sample. That sample is in column 1, so I'm going to select column 1, and I have to tell it the known population standard deviation, which was 2. I choose options. We wanted a 90% confidence level. Minitab prefers that you type 90.0 or 99.0. If you don't put the 0.0, it's not going to count it wrong. It just prefers it to be typed that way. The alternative hypothesis is always not equal. We click OK twice. And my results appear the same way as they did before. One of the benefits is I now have the mean for that list of 22 data values. I also have the standard deviation, and I have the adjusted or the central limit theorem standard deviation. So at the end of this, I can see that my lower bound is 4.799. The upper bound is 6.201. I need to find the error bound for the population mean. So that's a manual calculation. Upper bound minus lower bound divided by 2. So I have 6.201 minus 4.799 divided by 2. So getting my calculator, 6.201 minus 4.799 is 1.402 divided by 2 is 0.701. So my margin of error, or error bound for the mean, is 0.701. So we could be off by that much. Then we write our conclusion. We estimate with 90% confidence that the true population mean pop quiz statistics score is between 4.799 and 6.201. Questions? I want to skip the fourth example for just a minute, and we have about 16 minutes left, and I want to go down and talk about the sample size estimate. Okay, so I want to talk about the sample size estimate. Again, the idea behind the sample size estimate is to make sure that we collect enough data so that when we conduct our analysis, we have a particular or a specified margin of error. You know, maybe I only want to have a 5% margin of error, or I want to have only a 3% or 1%. How many people or how many items should be included in the sample to ensure that I have enough to fall within that particular margin of error? So with the confidence intervals, again, the scenarios are going to pretty much give you all of the information. You have a particular desired margin of error. You're given the population standard deviation. We do have to talk about the critical value for that confidence level. Minitab's been doing that behind the scenes for us. But we have to use that particular value in the calculations. And again, Minitab doesn't calculate this sample size estimate. I've given you the formula. The formula is the sample size equals your critical value times the standard deviation divided by the margin of error, and then that whole quantity is squared. One of the things, again, to ensure that we are within that particular confidence level, we do always round up if the answer is not a whole number. So if you get a decimal number, you're always going to round up. Having one extra is better than not having enough. To determine your critical value, I've given you a table of those values. And it does look funky. That symbol looks kind of funky. It's the letter Z because it's coming from the normal distribution. The subscript is alpha over 2. And again, that goes back to that idea of our normal distribution, where that we have those regions in either tail, and the probability of the failure is being divided between those two regions. That's why it says alpha divided by 2. It's just a notation. Don't get caught up. But I highlighted or bolded I really should have another one bolded. Let me see if I can bold it for you. Okay, 99% is also one that you really will see a lot. So those are the 3 most popular that you'll see. And so this gives you the critical value without you having to go look it up on some extra table. I believe, and I'll double check that this is the case, I believe this table is part of the header at the beginning of the midterm exam so that you don't have to memorize these numbers. Okay, so let's look at an example of how this works. Okay, so I'm going to skip example 4 and I'm going to go down to example 5. It says, suppose scores on exams in statistics are normally distributed with an unknown population mean and a population standard deviation of 3 points. How many scores would the professor need so that a 90% confidence level would have a margin of error of 0.5 points? Again, notice it tells us several things here. One, it tells us that we are dealing with a normal distribution. Okay. It also tells us that our population standard deviation is 3 points. It tells us we want to have a 90% confidence level and that our margin of error is 0.5 points. So again, everything we need is given in the problem because we need the margin of error, we need the population standard deviation, we need the confidence level because that confidence level is going to lead us to the critical value. Okay, and then from there, we're able to do the calculations because it's just a straight out plug and chug into the formula. So let's see. My margin of error is 0.5 points. Standard deviation was 3. My confidence level is 90%. And if I go back to that table, 90%, my corresponding Z value is 1.65. So my Z is 1.65. So I'm going to substitute into the formula. The formula is this: my sample size equals the critical value times the standard deviation divided by the margin of error, and that entire value is squared. So guys, it's a straight out plug and chug. You have or have been able to identify all of the numbers. So if I do this, I have my critical value is 1.65. My standard deviation is 3. My margin of error is 0.5. And that whole value has to be squared. Okay, so I'm going to do the math. 1.65 times 3, I'm going to write it out, is 4.95 divided by 0.5. So 4.95 divided by 0.5. Oops, sorry, I did 0.05. is 9.9, and 9.9 squared is 98.01. We automatically round up regardless, so 99. So it would take at least a minimum of 99 student scores to be within a 0.5% margin of error in this scenario. Now, all of those calculations are done manually, but all of the numbers that you need are in the problem. All right, let's do one more of those. A researcher is interested in estimating the mean monthly salary of sports reporters in a large city. She wants to be 95% confident that her estimate is correct. Assume the standard deviation is 1100. How large a sample is needed to get the desired information and to be accurate within $150. Okay. It doesn't really tell us that it's going to be a simple random sample, nor does it really tell us, of course, we're trying to calculate the sample size. Okay, but we're going to go for it. Again, you should be given in the story, you should be given your margin of error, your population standard deviation, your confidence level, which ultimately leads you to your critical value. So reading back through this, she wants to be 95%. So my confidence level, well, let's see. My confidence level is 95%. From the table that Miss Ralston has provided, 95% is 1.96 for my critical value. My standard deviation, it says to assume it is 1100. And we want my margin of error to be $150. Again, don't overthink this, guys. You just have to recognize that you're calculating that sample size, and the formula for sample size or the population is the critical value times the standard deviation, all divided by the margin of error, and that entire quantity is squared. Plug and chug. Do not overthink this. So we would have 1.96 times the standard deviation divided by the margin of error, and then that can be squared. So 1.96 times 1100 is 2156 divided by 150, and that's squared. So 2156 divided by 150 is 14.373 repeating. We're going to square it, which gives me 206.592711, and it keeps going. So again, I'm going to round this, and it's going to round to 207 people. Again, it's better to have one too many than not to have enough. Questions, thoughts, concerns? You are not ready to do the quiz for confidence intervals. We still have to talk about confidence intervals for proportions, and we still need to talk about t-intervals. What is due this Sunday is quiz 5, which is over the central limit theorem that we talked about on Tuesday. So do you have questions? Got a thumbs up, so y'all must all be good. All right, I hope y'all have a good weekend, and I will see you on Tuesday.